Welcome back to the deep dive. Today we are going to dismantle a very specific, I guess you could say a very human assumption that I think we have all, projected onto artificial intelligence.
Oh, absolutely. We anthropomorphize these models all the time.
We really do. And this assumption, it comes directly from how we were taught in school. So think back to taking a math test. You know the drill, right? Show your work.
Yeah, the golden rule of middle school math. I mean, if you just wrote the correct answer down, you got 0 points.
Exactly.
You had to prove the struggle. You had to show every single step.
Right, and it went way beyond math, too. Think about writing an essay on, say, The Great Gatsby. If you didn't really know what the green light symbolized, what did you do?
You wrote a lot.
You wrote a lot. You expanded on the premise. You threw in big, flowery words. You just wrote paragraph after paragraph, hoping that somewhere in that massive wall of text, a coherent thought would magically appear, and the teacher would give you a B-.
Yeah, the classic spray and pray method. I think we've all been there at like 2 a.m. the night before a paper's due.
We have. And because of that shared trauma, we have this built-in bias. We naturally assume that if someone or something is writing a really long, detailed response, they must be thinking really hard.
Right. We conflate length with effort, and we conflate effort with intelligence.
Exactly. And naturally, when we started building these massive AI models, we just applied that exact same logic to them. We assumed that if a model writes a literal novella to answer a question, it must be doing some serious cognitive heavy lifting.
Which feels super intuitive, right? If you ask a complex question about quantum physics and you get a 2-sentence answer,
Yeah.
you feel shortchanged. But if it spits out 5 paragraphs breaking everything down, you trust it more.
You assume it thought more about it.
Right.
But, and here's where it gets really interesting, we are looking at a new paper today from researchers at the University of Virginia and Google, and it says our intuition is just dead wrong.
Completely wrong.
In fact, it suggests that in the world of large language models, verbosity might actually be a symptom of failure.
It is such a fascinating piece of research. The paper is titled Think Deep, Not Just Long, and it fundamentally challenges the current gold standard in AI reasoning. They've essentially found a way to mathematically distinguish between an AI that is genuinely reasoning and an AI that is just yapping.
A yapping detector. I love that.
It basically is. It's a lie detector for digital rambling. They can distinguish between actual internal cognitive effort and mere, verbosity.
And that distinction is crucial for you listening because, as we're going to see, it's not just about getting the right answer. It's about saving companies millions of dollars in compute costs.
Oh, massive amounts of money.
So our mission today is to unpack this new metric they've developed. It's called the deep thinking ratio. We're going to look under the hood of these models to see what thinking actually looks like at a digital level and why the chain of thought method we've all been celebrating might need a really serious upgrade.
Yeah, it's going to totally change how you look at every ChatGPT response you get from now on.
So let's dive in. To set the stage, we have to talk about the status quo. For the last couple of years, the absolute gold standard in AI prompting has been chain of thought. If you're playing around with these tools, you probably know this one.
Right, this was the big breakthrough in prompt engineering a while back. We realized pretty early on that if you ask an AI a really hard math problem and just say, "What is the answer?" it often just faceplants.
It tries to jump straight to the finish line.
Exactly. It hallucinates. But if you tell the model, hey, think step by step, or explain your reasoning before answering, the accuracy shoots through the roof.
It needs to talk it out. Just like that middle school math test, it needs to show its work to get the credit.
Right, because generating the text breaks the problem down into manageable chunks. And because this works so well, the whole industry just adopted this more is better mindset.
If 10 steps are good,
20 steps must be better. 50 steps must mean the AI is a genius. We started using token count, which is literally just the length of the response, as a proxy for how hard the model was working.
length equals intelligence. That was the equation.
That was the equation. And this is exactly where the researchers from UVA and Google stepped in and said, hold on a second. Is that actually true?
So what did they do?
They decided to run these models against some incredibly difficult benchmarks. We're talking about the AM, which is a competition-level math exam for high school geniuses, and the GPQA.
The graduate level science questions, right?
Yes. These aren't, asking for a chocolate chip cookie recipe. These are real brain busters.
Okay, so they take these ridiculously hard tests, and they look at the relationship between the length of the AI's answer, of the token count, and whether the answer was actually right. What did the data show?
They found a negative correlation.
Negative.
Significant negative correlation. Specific across these hard reasoning tasks, they found an average correlation of negative 0.59.
Whoa. Okay, let's just pause on that number for a second. Negative 0.59. That's not just statistical noise. That's a loud signal. That basically says the longer the answer is, the more likely the AI is completely wrong.
Precisely. If your AI is writing a dissertation to answer a math problem, it's probably lost. It is a giant red flag.
That is, oh, it's the exact opposite of what I would expect, but it makes perfect sense if you go back to that student in the exam hall. If you know the answer is E equals MC squared, you just write E equals MC squared.
Right.
But if you don't know the answer, you write 3 pages about the nature of energy and the history of light bulbs, hoping for partial credit.
That's the spray and pray approach in action.
But why does the AI do that? Humans do it because we're trying to trick a teacher. Why does a machine spiral into these long answers when it's confused?
The researchers describe it as a sort of doom loop. You have to remember how these models actually work. They are just predicting the next word based on the words that came before.
Right.
So let's say the model starts with a flawed heuristic. Maybe it makes a bad shortcut or a wrong assumption in the very first sentence.
Okay, so it starts on the wrong foot.
Right. But now that wrong foot is literally part of the text it just generated. So the model treats its own mistake as a fact.
Oh, wow.
It tries to justify it. It amplifies the error. It starts to realize the math isn't working out, so it adds more steps to try and fix it. But the foundation is already rotten.
It's digging a deeper hole.
Exactly. It goes down a rabbit hole of irrelevant details, spinning its wheels, and suddenly you have 2,000 words of absolute gibberish.
So it's not thinking hard at all. It's overthinking. It's almost like anxiety masquerading as analysis.
That's a really great way to put it. It's prioritizing output volume over internal clarity. And this is a total nightmare for developers. You have to realize you are paying for every single word that model generates.
Right, the compute costs.
If 80% of those words are just the model confusing itself, you are burning money for a worse result.
So we obviously need a better way to measure effort. We can't trust the output length because the model can filibuster.
Right.
We need to somehow see what's happening inside the AI's brain. And I think this brings us to the core innovation of this paper, which is the deep thinking ratio, or DTR.
But DTR, this is the real game changer here.
How do we measure thinking if we can't just look at the text it spits out? How do we actually get inside the machine?
So to understand DTR, we have to get a little bit technical about how large language models are built. So we usually treat them as black boxes. You know, text goes in, magic happens, text comes out.
Yeah, that's how most of us use it.
But inside, there is a very specific structure. It's layered.
Okay, walk us through these layers, because usually when I hear the phrase neural network, my eyes just glaze over, so give me an analogy.
Fair enough. Imagine a stack of translucent sheets. Let's say there are 36 of them stacked directly on top of each other. When you feed information into the model your prompt, it doesn't just instantly jump to the answer. The data flows from the bottom sheet, layer 1, up through the stack all the way to layer 36.
So it's like an elevator ride.
Exactly like an elevator ride. And at each floor or each layer, the model is processing, refining, and transforming that information. It's adding context, it's checking grammar, it's doing logic. By the time it hits that top floor, layer 36, it's finally ready to spit out a word.
So layer 1 is the raw input, and layer 36 is the final polish before it actually speaks.
Roughly, yes.
Yeah.
Now here's the magic trick this paper utilizes. You can actually probe the model. You can pause that elevator ride at any floor.
Really?
Yeah, you can stop it at layer 10 and ask, hey, right now, based on what you've processed so far, what do you think the next word is going to be?
So you can literally see the rough draft before it's published. You can see the thought forming in real time.
You can see the indecision. That's the key. And what they found is that different types of words behave very differently as they move up those layers.
Give me an example. What does an easy word look like in this elevator?
Take functional words. Words like though, is, or standard formatting words like boxed in a math solution, or maybe completing a super common phrase like once upon a time.
Time!
Exactly. For those words, the model makes up its mind very early. By layer 5 or layer 10, it's 99% sure the word is time, and it stakes time all the way up to layer 36. It's perfectly stable.
So that's a shallow thought. It doesn't require deep processing because the answer is obvious.
Correct. It stabilizes early. The elevator ride is boring because it knows the destination immediately. But then you have the hard tokens.
Okay, what are those?
These are the complex reasoning steps. Maybe it's a specific number in a difficult calculation or a logical operator or the final answer to a riddle. For these tokens, the model is actually fighting with itself.
Fighting with itself.
Well, statistically speaking, at layer 10, it might think the answer is 7. But by layer 20, as it integrates more context from your prompt, it shifts to 12. Then at layer 30, it realizes a constraint it missed earlier and switches to 13.
Wow.
It doesn't settle until the very deep layers.
That's fascinating. So the easy words cool down and harden instantly.
Yeah.
The hard words, the actual thinking, stay hot and fluid until the last possible second.
Precisely. The researchers call this late settling. And this is exactly what the deep thinking ratio measures. It's simply the percentage of tokens in a response that are late settlers.
So a high DTR means the model was struggling in a good way with a lot of the content. It was using the full depth of its neural network to figure things out.
Yes. A high DPR implies high cognitive load. A low DPR means the model was basically on autopilot, effectively just reciting patterns it already knows well.
It's the difference between reciting a poem you memorized, low DTR, you know the next word immediately, versus trying to formulate a complex argument in a live debate where you are frantically searching for the right concept until the exact moment you speak.
That is the perfect analogy. And this gives us a mathematical way to separate the wheat from the chaff. If an AI writes a 5,000-word response, but the DTR is only 5%, it means it's just rambling. It wasn't doing the heavy lifting.
Right.
But if it writes a 500-word response with a DTR of 40%, those 500 words were hard-earned.
I want to visualize this for you listening.
Yeah.
The paper actually talks about heat maps of thought.
Yes, they generated these incredible visual representations. Imagine looking at the text the AI generated, but you color code the words. The words that the model figured out early, the easy ones, are colored blue.
Okay.
The words that it kept changing its mind about until the deep layers are red.
So a smart answer looks red and hot.
A reasoned answer looks red and hot.
Right.
A yapping answer looks cold and blue. It's literally a thermal image of the AI's effort.
Okay, so the theory is solid. It makes total intuitive sense. But does it actually predict accuracy? Because that's the trillion-dollar question here. Just because the model is struggling doesn't necessarily mean it's right, does it? It could just be struggling because it's hopelessly confused.
That's exactly what they had to test.
Yeah.
So they compared DPR against the old metrics,
Yeah.
length, which we already know fails,
Yeah.
and confidence.
Confidence being how sure the model says it is.
Right, the log probability. Now, confidence was better than length. It did have a positive correlation, but it's super inconsistent because models are famous for being confidently wrong.
Oh, absolutely. I am 100% sure the answer is 4. Narrator, the answer was not 4. We see that all the time.
Exactly. The AI mansplaining phenomenon. But DTR. The deep thinking ratio had a remarkably strong, consistent positive correlation with accuracy.
Oh, strong.
Across all the hard benchmarks, the average correlation was 0.683. And on the specific math benchmark, AEME 2025, it went up to 0.941.
0.941. That is astronomically high for this kind of data. That's nearly a perfect predictor.
It is. It suggests that this internal struggle, this late settling behavior, is the single most reliable signal we have that the model's actually on the right track.
Yeah.
A way better predictor of truth than the model's own confidence score.
There was a specific example in the paper that really brought this home for me. It was a geometry problem from that AIM dataset. Something about tangent circles and rectangles. Classic nightmare fuel for high school math students.
Oh yeah, this example is the smoking gun of the entire research paper. They prompted the model to solve this geometry problem. It generated multiple attempts. One was completely wrong and one was right.
Let's look at the wrong one first. What did it look like?
It was a monster.
Hmm.
The wrong response was 27,724 tokens long.
27,000 tokens. Just for some context, The Great Gatsby is roughly 50,000 words. So this AI generated a short book to answer one math problem.
It really did. And if you read through it, it's just painful. The model sets up a coordinate system. Then it realizes that's too hard, so it tries to reset.
Oh, no.
It gets totally lost in the algebra. It starts iterating on numbers that don't even make sense. It's spiraling. It's just outputting text to stay alive at that point.
And what was the deep thinking ratio for that novella?
It was incredibly low, 13.9%.
So despite writing a book, very few of those words required deep thought. It was mostly just shallow procedural filler.
Exactly. It was a sea of blue text, just filler to delay the inevitable failure.
And the right answer, what did that look like?
The right answer was only 3,725 tokens. Still detailed, because it's a hard problem, but it was 7 times shorter than the wrong one, and the DTR, 19.0%.
Higher thinking density.
Much higher. Every step counted. It didn't waste time spinning its wheels.
Mm.
This essentially proves the thesis. Thinking hard, which means a high DTR, is efficient. Thinking long is often just noise.
This feels like a huge paradigm shift.
Yeah.
We've been training these models to be chatty, thinking that chatty meant smart, but we might have just been training them to be, well, bullshit artists.
We incentivize the exact wrong metric. We taught them to fill the page just like that desperate student. And this brings us to the application, because this isn't just some neat academic theory. This has huge real-world implications for how we run these models in production.
Right, because running a 27,000 token output costs real money. If you're Google or OpenAI, you do not want your servers tied up generating novellas of nonsense.
Exactly. And it's not just generating one answer. To get the absolute best results on these hard problems, engineers currently use a technique called self-consistency or majority voting.
Explain how that works for us.
It's basically brute force. You don't ask the model the question once. You ask it to generate, say, 48 different answers to the exact same question.
Yep.
Then you check which answer appears the most. If 30 of them say 42 and 18 of them say 5, you just go with 42.
So you're crowdsourcing the AI against itself, but wait, that means you're paying for 48 full generations.
Yes, it's incredibly expensive and really slow. And remember, some of those 48 answers are going to be those 27,000 token disasters. You are paying for all of that waste.
So how does the deep thinking ratio fix this?
The researchers proposed a strategy called Think It In. The idea is simple. Instead of treating all 48 answers as equal votes, we should rank them by their DTR. We should only listen to the answers that actually thought harder.
Okay, so you generate the 48 answers, you check the DTR for each, and you just toss out the ones that were yapping.
You could do that, but they found an even bigger hack. And this is the part that really blew my mind. They discovered that the DTR signal shows up early. You don't even need to generate the whole answer to know if the model is thinking deeply.
Wait, really? How early?
You can estimate the DTR just by looking at the first 50 tokens.
50 tokens? That's barely 2 sentences. That's just the intro paragraph.
It's just the start.
Yeah.
If the model is locked in and reasoning correctly, the heat shows up in the layers immediately. But if it's about to spiral into a hallucination, the layers look cold right from the very start.
That is wild. It's like being on a first date or a job interview. You know in the first 30 seconds if it's going to work out. You don't need to sit through the whole hour.
Exactly. So with this Think It End method, they start generating the 48 answers. But after just 50 tokens, they check the DTR. If it's too low, if the model isn't thinking hard enough, they just cut it off. They kill the process right there. They only let the deep thinkers finish writing.
That is brilliant. You're not just filtering the output, you're filtering the process. You're weeding out the lazy thinkers before they waste your time and your money.
And the results are massive. They found they could match the accuracy of the standard majority voting method, but they reduced the inference cost, the computing power required, by approximately 50%.
You cut the bill in half. In this industry where everyone is fighting tooth and nail for GPU availability and energy costs are skyrocketing, saving 50% is a game changer.
And you get the answer faster, too. Latency goes down because you aren't waiting around for the slow, dumb answers to finish generating. It creates a much snappier, smarter system overall.
It really highlights how inefficient our current methods have been. We've just been using this spray and pray method, generating massive amounts of text and hoping for the best. This new method feels like precision surgery.
It really moves us away from scaling by just adding more volume to scaling by adding more intelligence. We are finally optimizing for the quality of the thought, not just the quantity of the words.
It also makes me wonder about the future of how these models are built. If we know that late settling is the clear signature of intelligence, can we build models that are forced to settle late? Like, can we bake this into the training data?
That is absolutely the next frontier. Right now, we are just using DTR as a filter. But you're right, could we use it as a reward signal during training? Could we teach the model, hey, don't just predict the next word easily. Struggle with it. Liberate.
It really humanizes the machine in a strange way. We tend to think of computers as instant. You press a button, you get a result. 2 + 2 is 4, instantly. But this research shows that for the really hard stuff, the struggle is necessary. The hesitation, the revision, the internal debate, that is where the intelligence lives.
It actually brings up a fairly profound philosophical question, if you
Sure.
think about it. The paper frames this purely as computational effort. It's math. It's just probability distributions shifting across neural layers.
Right.
But if we look at what's really happening, a token stays unsettled. It starts as one idea, it gets challenged by the next layer, it gets revised, and it finally settles on a truth only after passing through 36 stages of rigorous scrutiny. Is that just a calculation? Or are we seeing a digital form of actual deliberation?
That is the heavy question. When you or I think, we propose a solution in our heads, we reject it, we refine it, and then we settle. We call that human reasoning. When the machine does it, we call it late settling. But are they really that different?
The line is definitely getting blurry. And as these models get bigger and deeper, that internal process is only going to get more complex.
Right.
We might eventually find that thinking isn't some magical biological property, but just a fundamental property of information processing that requires a certain amount of friction.
Friction is a great word for it. Thinking requires resistance. If it's too easy, if you know the answer instantly, you're probably not thinking. You're just recalling.
Exactly. Real thought is messy. And now we know that even for machines, messiness, at least internal messiness, is a sign of high intelligence.
So the next time you see an AI write a massive, winding answer to a simple question, don't be impressed by the word count. Be suspicious. It might just be the digital equivalent of a student trying to hit a word limit because they completely forgot to study.
And if you happen to have the developer controls, maybe tell it to stop yapping and think a little deeper.
I love it. We are going to wrap it up there for today. This has been a truly fascinating look into the brain of the machine. Thanks for joining us on this deep dive.
Always a pleasure to be here.
Keep looking beneath the surface, everyone. We'll see you next time.